Hello and welcome back to my channel. Today's gonna be a quick video revising the basics of organic chemistry basically, and in this video the topics discussed will be all about hydrocarbons, or basically the basics of hydrocarbons and how to name a hydrocarbon. And the hydrocarbons we're going to be focusing on in this video are alkanes and alkenes and isomerism in both. So that's why I was saying it's only the basics. I'm not going to be discussing how to produce any hydrocarbon or anything like that. And yeah, let's get started. For more details on this video, check the description box below. So organic chemistry basically focuses a lot on organic compounds, and organic compounds are compounds that contain carbon. And a branch of organic compounds are hydrocarbons, and these are compounds containing only hydrogen and carbon. So if, for example, the compound contains hydrogen, carbon, and nitrogen, it's not called a hydrocarbon anymore. It's now just an organic compound because it contains carbon. So the biggest rule about hydrocarbons is that it should only contain hydrogen and carbons, and this is very important. So here are the hydrocarbons we're going to be focusing on. There are two types of hydrocarbons: open-chained hydrocarbons and closed-chained hydrocarbons. What this basically means is that open-chained hydrocarbons are open-ended. They have two ends, and they are basically in a long line, and they're not in a circle like cyclic hydrocarbons or closed-chain hydrocarbons, where, as you can see, all the carbons are bonded together in a circle and the hydrogens are just coming out of the carbons like this. So that's the difference between open-chained and closed-chained. Now we're going to be focusing more on open-chained, and open-chained hydrocarbons have two branches too. The first one is saturated hydrocarbons, and these are hydrocarbons that have a single covalent bond between carbon atoms. And what that basically means is that any hydrocarbon that contains a single covalent bond between the carbons, we call that hydrocarbon an alkane or a saturated hydrocarbon. However, there's also another section to open-chained hydrocarbons, and that is unsaturated hydrocarbons. And these hydrocarbons contain double bonds between the carbon atoms, or even triple bonds between them. And the ones that contain double bonds are called alkenes, and the ones that contain triple bonds are called alkynes. And both alkenes and alkynes are unsaturated hydrocarbons. So as you can see, stated below, saturated hydrocarbons are hydrocarbons with only single covalent bonds between the carbon atoms, as shown here, and unsaturated hydrocarbons are hydrocarbons with double or triple covalent bonds between carbon atoms, as seen here. Okay, so we need to talk more about carbon, since hydrocarbons contain carbon, of course, and carbon is very important. So we're going to be talking about the carbon atom and how covalent bonds are formed in the carbon atom. So a carbon atom contains 6 electrons in total, and when we write the electronic configuration of carbon, it's written 2,4, since the first shell can contain a maximum of 2 electrons, and so the rest of the electrons will be in the second shell. And we know that any atom that has not completed its valence shell is very reactive, and it will try to react with other atoms to complete its valence shell. So as you can see here, carbon does not have a completed valence shell. So the number of electrons left for it to be completed is 4 more electrons, and carbon here is a nonmetal, so it will form covalent bonds with other nonmetals. And what that basically means is that the carbon will try to share its electrons with other nonmetals to complete its valence shell. So this is a carbon atom and its valence shells, and as you can see, there are 4 electrons here, and we need 4 more to complete the valence shell here to make 8 carbons in that shell. So here is the first bond we're going to be talking about. This is a single covalent bond between two carbon atoms, right? And this is stated like this. So what happens here is that this carbon, where the electrons in this carbon is represented by X's, is sharing one of its electrons with another carbon, and this carbon's electrons is stated with this circle. So it's sharing one electron, and so this carbon needs to share another electron. So like that, the carbon gains another electron by sharing. So if we count here, that makes it 1, 2, 3, 4, 5. So it will need 3 more electrons. So to complete its valence shell, it will have to react with 3 hydrogens, and each hydrogen will share its only electron with the carbon, and this is shown by this circle, the blue circle. And yeah, so there are single covalent bonds between each hydrogen atom to complete the carbon's valence shell. So that's a single covalent bond. A double covalent bond, however, looks like this, where each carbon atom shares 2 of its electrons. So as you can see, this carbon is trying to complete its valence shell, so it shared 2 of its electrons, and in turn it gained 2 other electrons. That means that now this carbon has 4 electrons, and of course it has its own electrons. So it has 1, 2, 3, 4, then the others that it gained, so 5, 6. That means it needs 1 more electron. That means that this carbon is going to need 2 more electrons to complete its valence shell. So what it's going to do is it's going to covalently bond with another hydrogen, its first hydrogen actually. So this hydrogen here, and now it gains 1, 2, 3, 4, 5, 6, 7. It needs 1 more, so I'm going to add 1 more hydrogen here, and there you go. Now this carbon has its valence shell completed, and it's not going to react anymore. If we count here, this carbon of course has 4 electrons of its own, so it's 1, 2, 3, 4, and it gained 1, 2, 3, 4, and now it has a full shell. And this carbon is going to do the same thing, and of course the same thing can happen if this carbon has shared 3 of its electrons and this one has shared 3 of its own, except this carbon is going to bond with 1 hydrogen and not 2. But since today we're talking about alkanes and alkenes, we're talking only about a single covalent bond and a double covalent bond. The most important thing that we evaluate from this and what we've just discussed is that a carbon needs 4 covalent bonds to complete its outer shell. So it needs 1, 2, 3, 4, or it could look something like this: 1, 2, 3, 4. So yeah, these lines represent a single covalent bond, so 2 pairs of electrons shared between 2 atoms, and 2 lines dictate that it's a double covalent bond, and 2 pairs of electrons are shared between 2 atoms. What you need to look at basically is the amount of lines that the carbon atom has. If it has 4, then it is complete and you don't need to do anything else. The next thing you need to know is a functional group. And a functional group is an atom or group of atoms which is responsible for the characteristic reactions of a particular homologous series. What that basically means is that a functional group is basically a characteristic of a compound that makes it unique or different than other compounds. So if we look here at alkanes and alkenes, what's very obvious is that alkanes have single covalent bonds and alkenes have double covalent bonds. So we can say that the amount of bonds a compound has is its functional group. So what makes alkenes unique is having double covalent bonds, at least one double covalent bond between carbon atoms. The same thing here with alkynes. It needs to have at least one triple covalent bond between the carbons for its functional group to be a triple covalent bond. we're not going to be talking about alcohols, but alcohol's functional groups is having OH in its compound, and this makes it unique from other compounds. That's what makes it different, So every compound has what makes it unique, and what that means is anything that makes it unique is its functional group, whether it's an atom or a group of atoms or covalent bonds between the carbons. The next thing is a homologous series. So a homologous series basically is a family of similar compounds with similar chemical properties due to the presence of same functional groups. So to make it easier, it's a group of compounds that have the same functional group. So whether that's a single covalent bond or a double covalent bond or a triple covalent bond. So this family that has similar functional groups have similar chemical properties due to the presence of that functional group. So going back to our diagram here, so this makes alkanes a homologous series, because any compounds in the homologous series of alkenes will have only a single covalent bond between the carbons. And the same thing happens with alkenes and alkynes. Alkenes have a double covalent bond between the carbons, so any compound that has that function or that functional group is in the homologous series of alkenes, and so on. Now, what you need to know about every homologous series is that they share general characteristics between them, and these characteristics are the same general formula. So, for example, alkanes have the same general formula of CnH2n plus 2, where the 2 is the number of carbon atoms in the compound. We're gonna get back to what a formula is, but for now, we just need to know that every compound in a homologous series has, they all have the same formula here, which makes them different from other homologous series. The next one is having the same functional group, and of course we know that since compounds in the same homologous series have the same functional group. The next thing is consecutive members differ by CH2. Consecutive means after each other, so if we look here at methane, its consecutive member is ethane, and then the next consecutive member of alkanes is propane, and so on. So what basically means by they differ by CH2 is that if we subtract the number of carbons and hydrogens of consecutive members, so if I subtract the number of carbons and hydrogen in ethane from methane, we're going to find that the difference between them is a single carbon atom and 2 hydrogen atoms, and so on if we go down the group. The only rule is that they should be consecutive members, so they should be after each other in the same order, and I can't pick a member from here and then a member from there, because that's not going to give me the same results. This of course applies to all homologous series, so if you look at alkenes, we're going to find the same feature. The next feature is having similar chemical properties, and we've read here that this is because of having the same functional group. So this was kind of predictable. The next one is gradual change in physical properties. So if we look at the homologous series of alkanes, we're gonna see here that the first 4 members are gases, but then the 5th member is a liquid. And if we go down the homologous series of alkanes, we're going to find a change in the physical state. Physical state means whether it's solid, liquid, or gas. So finally, common methods of preparations. So it's how you prepare the compounds. So every homologous series has a common method of preparation between the compounds and its members basically, but we're not going to go into details about how to prepare, but you just need to know that. So next up in our list is how to name a hydrocarbon. Naming of organic compounds in general, they don't have to be hydrocarbons, has 2 parts. The prefix part, which is basically the first part of the name, is dictated by the number of carbon atoms. The second part, which is the last part of the name, is dictated by its functional group. So the name of the hydrocarbon or organic compound equals to the prefix plus the suffix. So the prefix dictated by the number of carbon atoms here. So as you can see, if the compound contains one carbon atom, it starts with the prefix meth or meth or whatever. It's meth, of course. The second thing is, if the number of carbon atoms is 2, then it starts with eth. 3 carbons prop, 4 carbons but, and so on. You have to learn this list of prefixes. But of course, with a lot of practice, it becomes easier to identify prefixes, because you get used to them. And of course, you can make relationships, so relations between the names. As you can see here, oct is 8, so it's just like an octopus. An octopus has 8 arms or legs. So yeah, you can make that easier for yourself. The next thing is the suffix, which is based on the series of organic compounds. So that means the homologous series. So if the compound is in the homologous series of alkanes, aka it has a single covalent bond, it ends with -ane. If it has a double covalent bond and it's in the series of alkenes, it ends with -ene, and same thing with alcohols and carboxylic acids. So if our compound contains a single carbon atom, it's going to start with meth, and then if it contains a single covalent bond between the carbons, it will end with -ane. So if you add them all together, it's called methane, and so on. You just keep looking between these two things and making up the names. So our first homologous series is the series of alkanes, and they have the general formula of CnH2n plus plus 2. So n is the number of carbon atoms. So what this basically means is that if, for example, I have a compound and it's an alkane and it contains 2 carbons, right? So the general formula is CnH2n plus n. Yeah, that's correct. So if it's an alkane and it has 2 carbon atoms, we're just going to substitute to find its formula. So it's C2H2 multiplied by 2 plus 2, and this gives us an answer of C2H6, I think. Yeah, okay, it's correct. So yeah, you can just substitute. All you need to know is the number of carbon atoms, and you're going to be able to find the whole molecular formula of that compound. So the first one, methane, it's also called natural gas, by the way, just for your knowledge. So you also need to know the difference between molecular formula, structure formula, and condensed formula. Molecular formula is basically a summary of the number of elements, of atoms, present in the structural formula. So you can look here, and methane contains a single carbon and then 4 hydrogens, so it's just gonna write it like that, very summarized. The structural formula shows you how it looks, how that methane looks, with the bonds here being the lines. So when the number of lines is 2, then it's a double covalent bond, and so on. So let's look at ethane while we understand what a condensed formula is. A condensed formula basically focuses on carbon atoms, each carbon atom being separate. And so first we're going to focus on this carbon atom. It has 3 hydrogens, so I'm going to write CH3, and then how is it connected to another carbon atom? It's connected with a single covalent bond, so I'm just going to do like that. And then the other carbon atom here looks like this, so it's CH3, so the condensed formula looks like this. So when you're doing the condensed formula, you basically think of every carbon atom being independent, and then you look at its hydrogens and stuff like that. So yeah, the same thing going down the group, and yeah, this looks like that. The second homologous series is called alkenes, and the functional group is having double covalent bond between carbons, and its formula is CnH2n. So when we have a number of 2 carbon atoms, we're just gonna multiply by 2 to get the hydrogen number, fairly easy. And because the functional group is having a double covalent bond between carbons, you cannot have methane, because methane, or just any compound that has meth in the beginning, will require one carbon atom only. And with a single carbon atom, you cannot have double bonds between carbon atoms. That doesn't make sense. So alkenes start with ethene, since that's when you have two carbons and you can start adding double covalent bonds. This is very important to know. So yeah, this is how it looks like. As you can see, it looks quite different from alkanes, and that's because if you zoom in, you're gonna see that here, the carbon here has a double covalent bond between a second carbon. So you can count the number of covalent bonds the carbon has. It has 1, 2, 3, 4, so we don't need to add a hydrogen here. The same thing is with this carbon. It has a double covalent bond and then 2 more bonds, so that's 1, 2, 3, 4. You don't need to add a 5th hydrogen bond here with the carbon, so it looks kind of different than alkanes. Of course, here the condensed formula, it follows the same structure like alkanes. You focus on carbon atoms and then the hydrogen sprouting from it, but when there's a covalent bond between the carbons, you're gonna add 2 lines. And yeah, one more thing you can notice is that even though the double bond here is at the very end of the compound seen in the structural formula, the condensed formula, it's written at the very beginning. And that's because when we write the condensed formula, we try to put the covalent bond at the very beginning. So when I'm doing the condensed formula, I look at where the covalent bond is and then count from that carbon atom. So I'm going to count this carbon atom, that's C2H, so that's like that, and then a double covalent bond, and then another CH, and then so on. So I'm going to go from the side that has the double covalent bond closer. The last thing we're going to be looking at is isomerism. So isomerism is basically compounds which have similar molecular formulas, or same molecular formulas but different structural formulas. So same molecular formulas means it has the same number of atoms of a certain element, but different structural formula, which means it looks different and the places of the elements and atoms are different than each other, are known as isomers, and this phenomena is known as isomerism. So isomers are basically compounds. There are 2 compounds or 3 compounds or so on. They all have same molecular formula but different structural formula. Isomers can have different physical or chemical properties, so that's important. You need to know that. We're going to be starting with isomers and alkanes. So the first 3 alkane members, which are methane, ethane, and propane, do not exhibit isomerism. And this is again very important, since they don't have enough carbon atoms for you to mess around with the structure, because for example, here in methane, you can't really change the structure. It just looks like that and you can't change it. In ethane, again, you can't really change the structure. And same thing with propane. You just don't have enough carbon atoms for you to change. And we're going to be looking more into that, and you're going to find out why. But we're going to start with butane. So that contains 4 carbon atoms and 10 hydrogen atoms. So a normal butane looks like this. It has the carbons and they all have single covalent bonds, and then hydrogen sprouting from it, and each carbon atom has 4 covalent bonds to complete their outer shell. And yeah, it just looks fine. But butane isomers look a bit different, and as you can see, what basically happened was we have taken one of the carbons and placed it in the middle carbon, and I will demonstrate that to make it easier. So here's butane, and what happened is that I will take any carbon atom from the very edge of the chain. So I will, for example, take this carbon, and when you take a carbon, you take all the hydrogens with it. Just think of a condensed formula. You're going to take the carbon and its hydrogens, and when I hide this like that, you're going to see that there are 3 carbon atoms left. We're gonna be looking at the middle one. So the middle one is of course the second one. So what will happen is that I will take this whole structure and I will place it here in place of one of those hydrogens. It's your choice, but it will basically be the same thing. So when that happens, I will change the hydrogen here. I will delete it, for example, or erase it, and then I will place the carbon first. I will, single covalent bond between the carbons, and then the hydrogen sprouting from it. So that's 3 hydrogens here. Now it looks like that. So to summarize it, a way of making isomers is by taking the carbon from the very edge of the chain and then placing that as a branch in the middle carbon atoms of the new chain here, the smaller chain. So this happens, and this is an isomer of butane. You need to know that this right here, this is called methyl. It's not methane. Methane has 4 hydrogens and methyl has 3 hydrogens. So the way I name this isomer is I will count where, first of all, I will actually look where is the tallest carbon chain. So I'll count here 1, 2, 3. So this chain has 3 carbons, and 1, 2, this chain has 2 carbons. So this is the bigger chain. I'll call this the parent chain. Okay, so this is the main place I'm going to be focusing on. So where on this chain is there a branch here? So I'll count 1, 2, 3. I'll count only the carbons here in the chain. We're not talking about the hydrogens. I'll also count from the other side. So that's 1, 2, 3. So if I count from both sides, the chain, or the branch, is on the second carbon atom. So the first part of the name is going to be 2. This indicates the place of the branch, where it is coming from the parent chain. And I will put a little dash here. And then now we're going to be naming the branch. And as we can see, this is CH3, so that's automatically methyl. And you should learn this, of course. So it is 2-methyl. So the second thing you're going to be doing is looking at the name of the chain, the branch coming out of the main chain. And then the third name is the name of the parent chain. So when we do this and we change the compounds here, so when isomers happen, basically, the chain becomes smaller and the name of the chain changes. So how many carbon atoms? 1, 2, 3. So that's pro or prop. And then there are single covalent bonds, so that's propane. So the parent chain is called propane. So isomers, 3 parts. This part is where in the main chain which carbon the branch is on. So that's the second one, you write 2, and then the second part is the branch name. Third part is the parent chain name. So here it is. This is butane and this is 2-methyl butane. They're both isomers. They both have the same number of atoms in a particular element, so they have the same molecular formula but different structural formula. Isomers of pentane. There are 3 isomers of pentane. There is normal pentane here, 5 carbon atoms, and then the hydrogens and single covalent bonds. And then there is 2-methyl butane, where the same thing in 2-methyl propane happens. We take a carbon atom from the very edge, then place it in one of the middle carbons. An important question is, if I take away one of the carbons, there will be 4 carbons. Where do I place the carbon branch? Because there will be 2 middle carbons. And this answer is anywhere. They just have to be the one of the 2 middle carbons here if it's an even number of carbons. So I can place it on this carbon or that carbon. Now in the naming here, the 2 here, we're going to count 1, 2, 3, 4, and then 1, 2, 3, 4. And as you can see, the branch is on 2 and 3. Which number do I pick? You have to make sure that you always pick the smaller number. So in this case, I'll pick 2 and not 3. So that's 2, and then methyl is the branch, and butane is the parent chain. So if I did the same thing and place the branch on this carbon atom instead, and then count this carbon atom here is 3, 2. So again, I will pick the smaller number. So again, it's 2-methylbutane. It wouldn't matter which carbon atom you put it on if it's an even chain here. The next isomer I did only exists in pentane and higher carbon numbers, since you need a lot of carbons to do what we're doing here. Butane could not do this because it does not have enough carbons to do this isomer, basically. So what happens here is that I took 2 carbon atoms from the edge instead of 1, and then when I take 2 away, there will be 3 carbons in the main chain. So I will place it in the very middle carbon here. I'll place 2 branches coming out of it, and as you can see, both of them are methyl, so there's no problem here. The problem comes in the naming. So we've said here that the 2 here before the little dash is the number or the position that the branches are on. So this 2 here represents which carbon atom it is on. So it is on the second carbon atom of the main chain, and then this number here, the first 2, is the number of branches on that carbon. So there are 2 branches here, so it is 2 and then comma and then 2 dash. The structure of the branches, this is methyl, this is also methyl. So I'll write methyl, but I'll instead write dimethyl, since there are 2 methyls in that branch, not only a single methyl. So it is 2 dimethyl, and then the parent chain is propane. So it's 2,2-dimethyl propane. Last thing, isomerisms in alkenes. So the first 2 members of alkenes, which are ethene and propene, do not exhibit isomerism, again because they don't have enough number of carbon atoms for us to change the structural formula of it. So the first thing we need to know is that we can do 2 isomers, and this can be done in alkenes by either changing the place of the carbon, just like we did in alkanes, or changing the position of the double bond. So here we're looking at butene. This butene here, we're always going to be focusing in alkenes on the position of the double bond. So here, when we count and we write here, so that's 1, 2, 3, 4, 1, 2, 3, 4. So I've numbered the carbon atoms from both sides. Where is the double bond on? So that's on this carbon atom here, and this one too, right? But since this one is closer to the edge, we're going to be looking at this one. So it's either the first or the fourth one. Again, we focus on the smaller number, so it is on the first carbon atom. So instead of writing only butene, to specify more about the carbon bond location, I will write 1-butene. Or you can write but1-ene. This is also okay. 2-butene or 2-butene says that the double bond is in the second carbon atom. So if we count again, so that's 1, 2, 3, 4, 1, 2, 3, 4 carbons. The double bond is in either 2, 3 or 2, 3. So I'll pick the smaller number. So it doesn't matter if I pick this one or this one, they're both going to be the same thing since I'm picking 2, and this is the position of the carbon bond, so that's 2-butene or 2-butene. So that's another isomer of butene. This one is 2-methyl or 2-methylpropene. This basically tells us that what we've done is we changed the position of one of the carbons. So I took one carbon from the parent chain and I put it in the middle carbon. Of course, when I take one here, 3 are going to be left, so the middle carbon is the second carbon always. So that's 1, 2, 3. We're going to put a chain or a branch here, and that's going to be methyl, and that's 2. The position is in the second carbon. Methyl is the name of the branch, and then propene, the name of the parent chain. As you can see, it's propene, 3 carbon atoms, and then a double covalent bond. So that's it. These are all the isomers here for alkenes. The same thing will happen for all the other alkenes. We can change up the position of the double bond or change up the position of one of the carbons. Thank you so much for watching. This was a kind of quick revision. I tried to make this video as short as possible. I hope you I hope this was helpful for you, and see you next time.